Hi, my name is Gideon Humphrey, and I run the undergraduate physics labs here at UTM. I've been asked to show you a couple of our more eye-catching demonstrations, so in this video we're going to get out our vortex gun and our superconductive levitation track. This is the first year lab. Right now it's sadly quite empty because of the current coronavirus safety measures, but it will give us a nice wide open space to work with. This is what the vortex gun looks like. We started with a reasonably large garbage can and sealed a plastic tarp over the open end with bungee cords. There's a zip tie handle that we can pull on. If we flip it over, we can see that there's a hole cut out of the bottom, and the plastic tarp is connected internally with more bungee cords such that the tension keeps the plastic tarp pulled inwards. This way, when we pull on the handle and release, the tarp will return to this equilibrium position and shoot out some of the contents of the garbage can. You can use the gun as is to shoot air, but we will use a fog machine to fill the garbage can so that you can see what's happening. While I'm filling the gun, what do you think will come out when I shoot it? A burst of smoke? A focused stream? Something else? When I shoot it, you can see that the result is a near-perfect smoke ring. This happens for a few reasons. One is that the hole that the fog comes out of doesn't extend all the way to the sides of the can. This sets the size of the ring, but it also means that the air on the ring's inside is moving faster than the air on its outside, causing the ring to constantly turn itself inside out. This has the effect of stabilizing its shape as it travels. If you could take a cross-section of the ring, what do you think you would see? To answer this question, we will turn out the lights and illuminate a cross-section of the smoke ring. Directing a laser through a glass cylinder converts the light from a beam shape to a plane, as you can see from the green line that ends up on the wall. With some fog in the air, you can see the air currents in the room interacting with the ceiling of laser light. We shoot the smoke rings such that they are approximately bisected by the plane of laser light, and if you look closely, you can see that each ring results in two spirals, rotating around and around on themselves as the ring travels forward. This is why the ring is able to maintain a cohesive shape, and this has implications for things like tropical storm stability. Our next demonstration is levitation, but before we get to that, I want to show you a very simple system that behaves in an unusual way. Here we have an aluminum pipe and two balls that look very similar but behave quite differently. The first one is stainless steel and doesn't really interact with the aluminum. The second one is a neodymium magnet, and although aluminum isn't ferromagnetic, it does have a property called diamagnetism, which causes the ball to travel rather slowly. What happens is that when the magnet moves relative to the pipe, it drives the electrons to move in eddy currents, and these eddy currents create their own magnetic field that pushes back against the moving magnet. Aluminum is an ordinary conductor, so the eddy currents will dissipate in the form of heat. However, if we had a superconductive pipe instead, the currents wouldn't die out, and we'd be able to make the magnet levitate in space. We don't have a superconductive pipe, but we do have a couple pieces of superconductor, inside the small black boxes shown, and a track made out of magnets. Our superconductors have a critical temperature of -80 degrees Celsius, meaning that they are only superconductive below that temperature. We will dip one in liquid nitrogen to cool it down so that we can work with it. If we then place it above the track, it will levitate there. It wants to resist any motion that results in a changing magnetic field, which means it is free to move along the track, but not up or down or radially. It also means that if we push the superconductor into a new orientation, it will lock into place and stay that way. It is possible to achieve a levitation height of a few centimeters this way. If we lift the edges to give it some speed, you can see that the same force levitating the object is also fairly good at preventing it from flying off the track. That is, the superconductor is held fairly strongly. If we flip the track upside down, we can show that it is even possible to make the superconductor levitate underneath the track. It may be worth mentioning that our superconductor boxes are open so that they can hold a bit of liquid nitrogen to stay cold longer, and when we do upside down levitation, it dumps out the liquid nitrogen. As such, we can't do upside down levitation for as long of a time period. I hope you've enjoyed these demonstrations. These and many other fun things are available to enthusiastic students, usually via joining the physics club. In normal years, the labs are buzzing with activity. Outside of lab hours, we have facilitated study groups, physics club, and open doors during business hours so you can study with other physics students. If you're looking to see what our more quantitative coursework experiments look like, please note that you can see our YouTube channel, UTM Physics, and look them up there. Thanks for watching, and I hope to see many of you next year.